Ooh, that's fine. I think the projector's off. Okay.
Okay, I'll just do the introduction. Okay. So our second speaker this afternoon is Yiannis from Jump Trading, where he's a hardware engineer. He's been with Jump Trading for the past 5 years. Before that, he worked at Huawei for 2 years in the CPU verification role after finishing his studies in advanced microelectronic systems engineering at the University of Bristol.
Right. Thanks for the introduction. Before we start the presentation, a couple of words about Jump. You guys might not know who Jump is or what we do. We are a proprietary trading firm. Got about 1,500 employees today. Pretty much worldwide, you'll find an office in every continent in most countries. We have an office in London, and we have our hardware site in Bristol, which is where we come in. Right? In terms of what Jump does, an algorithmic trading house, we just use computers to trade. There's very minimal human trading involved. And we want to use hardware to accelerate this, right? We want to be better at it, we want to be faster. Yeah, not much to say about this. You can look us up online or just talk to me afterwards if you need more info. So what's the point of this talk, right? We wanted to show how we accelerate delivery of our products. And this doesn't necessarily stop at verification, right? We're also responsible for bring up, and we're also responsible for getting stuff into production, right? And because we have a sort of high level view, we can execute a process that helps us deliver things faster, right? And this breaks down into 3 key steps. Step 1 is we have a unified software environment that we use for verification at system level and what we use for production. That's the same code that's running in both things. And we'll go into detail about how that's done. So to achieve this, you need a software stack that's compatible with both. And this might feel like it's obvious, but there's a lot of like peculiarities under the hood, right? If you're running on silicon, you probably want to initialize all of your memories to avoid parity errors. But if you're running in a simulation, you probably don't care about that, or you maybe do it once, right? Like that's the key idea. The second thing is, if you're going to be writing real software, as verification engineers, we don't naturally find ourselves writing good quality software most of the time, at least not to the standard of software engineering, right? Please don't shoot me. But yeah, you don't find yourself naturally doing this. And this is where having a software resource comes in. So you go to your software team and you say, hey, I'd like you to allocate someone to work side by side with me, help me write the software API such that you guys are happy with it. So whatever software API you use in simulation will become your production code. And by definition, it'll work, right? And then you have to address simulation speed challenges. You cannot spend billions of cycles programming an Ethernet PHY in a simulation. It's just not tractable. You'll never finish. So what do? You reduce the chip size. So if you have a design with 64 CPUs, you cut it down. You make the design have 4 CPUs, and you only use the 4. And you just run with the 64 once or twice and just live with it. You start preloading data. Things like loading ELFs into memories, that I think everyone does that. But also, if you need to write a routine to calibrate something, you just change the hardware such that in simulation, you only have to run the routine once. You don't have to run 100,000 iterations before it's appropriate to calibrate. And then finally, just use models for whatever component you can. Rip out the real PHY and just replace it with a model. You know, use the real PHY once at the end of your, just before tape out, run a simulation, make sure it's fine. That's it. These are some examples from our own internal stuff of how long it takes to do things. It takes about 5 billion cycles to program the PHY for Ethernet for real life. It takes about 4,000 in a simulation environment for us. Pretty much all of these happen in every single simulation that we have, and it's the same software code base. It recognizes that it's on silicon and it needs to run special routines. And by special routines, I mean it needs to run things like DC calibration, which you wouldn't necessarily care about in a simulation. All right, so that's part 1. Part 2, your verif engineers need to wear more hats. They have to be responsible for more things than just verification. So let's break that down. You have to be responsible for bring up, and you have to be responsible to sit there and be support for when we're deploying things into production. Why is that? It's because you're a fucking expert, right? Like, come on, you've worked on this thing. You've spent months, if not years, writing system level code for this thing. You know the most about it, right? Why would you then stop that knowledge base and say, all right, I'm not going to be involved in bringing up, some other guy's going to figure that out? No, you're responsible for it. You know everything, just carry on. And the same about going into production, right? Like, chances are whatever issues they're going to find, you've already identified them, or you already like bumped into them when you were writing code, when you were writing examples. Yeah, so you're involved from specification testing and initial programming routines all the way to just debugging why something has failed in production. Yeah, it makes sense. You are going to end up being in an exceptional spot to identify things that go wrong and collect feedback. And this goes beyond just collecting feedback, right? Because you'll wear the role of a software dev and you'll wear the role of someone who puts something in production. It's not just collecting the feedback, it's also how you deliver it, right? Because if you've got a design engineer called Bob and you want to suggest a change, you can just go to lunch with him and say, hey, dude, I want to change this. I don't like the control registers for this block. I need to change and support this. And that's a very soft touch thing. And I think there was a presentation earlier today that mentioned, how we're social beings who have to have a soft touch. That's much better compared to Bob waking up and finding that he's just got an email from the software team saying, we're struggling to use your control registers. Because that email is going to end up CC'd with like 6 hierarchies of managers going up and 6 hierarchies of managers coming down, and Bob's not going to have a good day. You can also make decisions that are going to impact schedule, right? And what do I mean by this? You might make a decision that says, you know what, I'm going to spend an extra week in verification at system level to write an appropriate API such that down the line, when I put this in production, they don't have to spend 3 weeks trying to write a software API for this from scratch, on the real silicon, because I have debugging capabilities. I can look at waves. I can pull the designer. I have all of those things available to me. So you make executive decisions, which you wouldn't normally be able to, right? Because why would you? If you're just a verification engineer, why would you inherently take an extra week? If I go to my boss and say that, he's going to look a bit funny, right? It's just, you're not going to do it. Yeah, covered that. So the final thing is your system level tests. They're going to have extra requirements because whatever you write has to be able to run both in simulation, it has to be able to run on silicon. And they have to match, and that doesn't always happen because simulation is a very sterile environment. If you think about a CPU, things like how warm the cache is or what code run on silicon before you run your test will have an impact. Whereas you never have that in simulation, or you don't usually. The other thing is analog models and CDCs can make this very challenging. No simulation ever tells you that when you have an Ethernet clock, it can be off by up to 100 parts per million. And that value will be different for one Ethernet and different for the other Ethernet, right? Yeah, it's hard to simulate, to replicate simulation predictability. This kind of just comes hand in hand. Simulation is like bang, bang, bang. That's not the case for real life. Your benchmarks are going to be very difficult to write. You have to understand everything that goes on in your system. Chances are, if they don't match, figuring out why they don't match is a very worthwhile exercise. Highly recommend everyone does it. You're going to lose your mind, but then you're going to experience a greater understanding of your chip. Yeah, and then finally, whatever test you write becomes an example for the end user, which we don't traditionally care about. But when you are in that role where you're also responsible for bringing up in the early phases of production, your examples will be what they use to put in production, right? How am I doing on time? Yeah, I'm doing all right. Okay, so I've been speaking for a long time and I've said a lot of things, but what's the actual results? I can't put bars on here, but this is in months and this is at 0. So these are 3 different ASICs that we put in production over the span of years. Very important to understand, these are in revisions. I'm not trying to sell you Rev A, B, and C of the same chip that we put in production. We're talking about very different beasts. Like you could describe one as a GPU, the other one's a CPU, and the other one's a stick of RAM, like completely different animals, right? But as we approach and we get better at understanding this methodology, we get better at putting this into production. And what happened here, we had our tests written in a way such that we didn't have to change them at all to run them during bring up. We got the first parts, came back to Bristol, and within a month we put them into production. And we're able to do that because our tests could run on silicon without any changes. our software users had already provided us with code that they were going to run in production. We knew what they wanted to run. We'd already run it. So by the time it came back, we had a few teething issues. I put the chip down in the wrong way around in the socket and burned the thing. Happens. But by and large, once we got past those early teething issues, that was it. It was working. We didn't have to debug many things. We had a couple of minor bugs that came out, but just by the sheer volume of soaking we could do. But yeah, we were successful. So we put our third generation thing into production within the span of a month. And then this slide, I have a personal gripe against presentations that don't tell you what's going to come around and screw you over. I won't say snake oil salesman, but yeah. This is very hard to put on a slide that you're going to show to a verification conference, but it's going to take longer, right? We've just discussed that you're going to have extra requirements on your tests, and you're just going to do all of this extra thing. It's going to take a bit longer, but hopefully you understand that it's a trade-off, right? You're going to trade off a bit of extra verification time, but you're not going to be in that stage where you're waiting for the software to be ready for the chip down the line. The moment it's ready to go, you throw in production. And although this says software developers, this should probably say software developers and senior management. You have to go and convince your management that this is a sensible approach, right? Because if they're used to this idea that you are a verif engineer and that's all you do and you don't do anything else, and you show up and you say, well, actually, I want to be in charge of both bring up and the early days of production, they're going to raise an eyebrow and say, well, justify it, explain it to me, why do you want this? So you have to get buy-in from them. And the software developers bit, it's because, they're like us, right? Like they have chips in production today. They have issues they want to debug. They have issues they want to fix. If you go to them and say, I need you to give me someone for a couple of weeks to work with me during system level verification, they're going to raise an eyebrow and say, well, I don't want to spend time on something that doesn't exist yet. So you need to get buy-in from people to make that work. And if you don't get the buy-in, then you can't make this methodology work. Yeah, that's it. I wanted to keep it short and brief. So here we are. And any questions from anyone?
Any questions?
So from the description of the verification, it's a pretty breadth of verification that needs to happen. One at unit integration, then user deployment level, and so on. Is it all bundled up, and the job role responsibility is just like 3 verification engineers into one kind of a thing as a job description perspective? Or I mean, in the sense that normally in traditional thing, these are just split up into multiple roles, and to go into the depth of expertise to go more into it. How would you trade a balance between the depth of expertise in each of the various stages of verification to just one verification going all the way up?
That's a very good question. I think of it as you can choose to have people who are dedicated to just block level verification, and that's all they do. And you can choose to have people who are dedicated to system level. You can choose to mix them. It's entirely up to you. But I view it as it's kind of better that it is separate, because you can then have a handover of knowledge where if at system level you say, right, I'm going to use this block for the first time, you go and grab, Bob from over there, and he comes to you and he says, this is the routine that I have in my test bench. And you have like a good reference point. And it also means that you as a system level engineer might not necessarily have to invest immense amount of hours to understand every peculiarity. You have the other guy who has built that expertise, and you can just rely on him. So I would lean more towards having different roles and different people, but I can see it working either way. I don't think it's like a hard requirement.
There's one question online about putting software engineers into the verification team the other way. Does that work? Have you tried it?
Yes, we have tried it. I think it works great. I think it helps educate both sides into the work that we do, right? And I think one of the pitfalls here is if you try and push a set of APIs that you've just written as a verification engineer, you try and push it into the software code base, they might come back to you and say, I don't understand any of this. Well, why is this necessary? because they weren't involved, right? So having an embedded software engineer into your team gives you someone who can say, right, this is done like this because the new bit of hardware needs it. So you gain an ally. And if they are involved in the verification and you're approaching tape out and it's crunch time and you need an extra pair of hands, you could make the move down and say, right, come and help. I need help. So yeah.
Hi. This kind of approach I've seen work really well in a domain-specific accelerator kinds of project where, in a way, you're co-designing compiler runtime hardware, and it's logical for the software guy to know quite a bit. But if you're delivering something to an ISA spec and there'll be external compiler writers and such, do you see it kind of playing out okay, or what's your thought?
We use an ISA internally, so I think, yeah, it works. And I think it works. I think you just have to perhaps you won't get access to the exact software that your customer is going to run down the line, but you will have access to the tool chain that they're probably going to use. So you can just say, right, I'm going to generate a lot of examples, maybe use something like CSmith to spit out multiple examples of this and just run it against your ASIC and just see, does it conform?
Okay, I think we'll finish there. Thank you very much.